Welcome back to bonding. Now we're on part 2. We're going to talk about covalent bonding and the differences between covalent and ionic. Let's go. Okay, covalent bonding is a type of chemical bond characterized by the sharing of pairs of electrons between atoms so that both acquire full octets. Not transfer, but share. They're formed between two nonmetals, so two things that are generally on the right-hand side of the periodic table, that have a relatively small difference in electronegativity. Nonpolar covalent have even electron sharing because there is a small to no difference in electronegativity values, somewhere between 0 and 0.4. Both atoms in the pair will have the same pull for the electrons and therefore will share the charge equally. Nonpolar means non-charged. Nonpolar means non-charged. Neither atom pulls more of the electrons than the other. Polar covalent molecules, so polar means charged, charged molecules have uneven electron sharing because there's a greater difference in electronegativity values, somewhere between 0.5 to 1.8. Again, this is a spectrum, so it's a little bit of a gray area where it starts and where it ends. One atom in the pair, the atom with the higher electronegativity value, or the greater ability to attract electrons, will pull a larger portion of the electron cloud to it and will have a partial negative charge. The one that is more electronegative has a partial negative charge, indicated by a delta minus. That's the Greek symbol letter D, actually Greek lowercase d, with a negative for the negative charge. The other atom will have less of the electron cloud and a partial positive charge. That's the Greek lowercase letter d with a little plus sign to indicate less electrons, more positive. Alright, so when you're drawing Lewis structures for covalent molecules, we're going to show the atoms connected with 1, 2, or 3 actual lines between them to indicate the number of shared pairs of electrons. Polar covalent bonds should include the partial charges, the delta plus and the delta minus, to indicate uneven electron sharing, but these symbols are frequently left off for the sake of brevity. They exist, but they're typically left off. I'm going to draw one really fast here, something like this, with a positive charge for the hydrogen and a partial negative charge for the chlorine, because the chlorine is more electronegative. Don't worry about Lewis structures at this point. We're going to have an entire video on all the different rules for making covalent bonds. So for the moment, what you need to see is there is a line to connect them to indicate shared electrons, and there are partial charges instead of full charges. So polar bonds versus polar molecules. Again, don't worry about this too much right now. We're going to have an entire video on polarity of bonds versus molecules. But for the moment, even if the bond between two atoms in a molecule is very polar, in other words, there's a large difference between the electronegativities of the two atoms, the molecule as a whole may be nonpolar. If it is symmetrical, the direction of the charges cancel and the molecule is nonpolar. If there's an uneven distribution of positive and negative charges, not symmetrical, the molecule is said to have a dipole moment and is considered to be a polar molecule. A dipole moment has opposite charges, dipole, two-pole charges, and it's considered to be a polar molecule. Don't worry about this so much right now. We're going to have an entire video on it later. This is just your basic introduction. Okay, next thing we have is bond order, bond energy, and bond length. We are also going to get into detail with this when we get into Lewis structures. Bond order is the number of bonds between the two atoms. A single bond has a bond order of 1. A double bond has a bond order of 2. A triple bond has a bond order of 3. There's actually a much more complicated technical definition, but the College Board doesn't care that you know that. This is all they want you to know about bond order. Bond energy is the energy required to break, not form, break a bond. The higher the bond order, the higher the bond energy, as it requires more energy to break a multiple bond. It would take more energy to break a triple bond than it would to take a single bond, break a single bond. So a bond order of 3 would require a greater bond energy. Bond length is the distance between the nucleuses of the two atoms involved in a bond. In other words, the length of the bond. The greater the bond order, the smaller the bond length. So a triple bond has a shorter length or a smaller distance between the atoms than a single bond. Atoms with a larger atomic radius have a greater bond length than atoms with a smaller atomic radius. Let's look at some examples of this. Okay, so this is carbon iodide, the carbon and iodine bond. So bond order of 1, because it's a single bond. Bond energy is 216, and bond length is 0.213 nanometers. So let's compare that to carbon and chlorine. So if you look at iodine and chlorine on the periodic table, notice that iodine has a larger atomic radius. Iodine is a larger atom than chlorine. So since it's a larger atom than chlorine, the bond length is also larger than the bond between carbon and chlorine. And it requires less energy to break the bond between carbon and iodine because the atoms are farther apart than it does to break the bond between carbon and chlorine. So oxygen, O2, we'll get to why later, but for the moment, O2, oxygen, is connected with a double bond. So this has a bond order of 2. Notice that a double bond brings the atoms closer together, a smaller bond length than the single bond, and requires a much larger energy to break. For nitrogen, the bond order is 3, which should tell you that there is a triple bond there, which means the atoms are even closer together and it requires even more energy to break that bond. Last thing, and for this one as well, we're going to get into a whole video on this later, so don't really concern yourself. This is just a basic introduction. Sigma versus pi bonds. These are both Greek letters, the Greek letter lowercase Greek s and p. Classified based on types of orbitals used in bonding. Sigma bonds result from hybridized s and p orbitals. They are the single or first bonds. Single bonds are sigma bonds. Pi bonds result from unhybridized p orbitals. It's called pi because they come from the p's. They are the second and third bonds. So if we look at the nitrogen from the slide before, one of these will be the sigma bond. The first bond is the sigma bond. The other two will both be pi bonds. If you had something like fluorine with one single bond, that would be a sigma. Sigma. And this is 2 pi. If you had something like oxygen from the one we were looking at before with a double bond, the first one is a sigma. It doesn't matter if the top one is the first one or the bottom one. Just one of them is a sigma. The other one is a pi. For the moment, don't think about why. We'll get into that later, but that's just your basic introduction. And that's it. That is your basic introduction to covalent bonding. I hope you had a good time and you join me next time for Lewis structures.